interferometer, which is a device with a beam splitter in here. You send in a beam of light input, beam splitter, and then the light, indeed, half of it gets reflected, half of it gets transmitted. Then you put a mirror here, mirror 1, you put a mirror 2 here, and this gets recombined into another beam splitter. And then, you know, if there would be just a light going in here, there would be two things going out. There's another one coming from the bottom. There will be two. There will be interference. So you put a detector D0 here and a detector D1 here to detect the light. So that's the sketch of the Mach-Zehnder interferometer, beam splitters and mirrors. Take a beam, split the light, go down, up, and then recombine it and go into detectors. You can get, and this is was invented by these two people independently, 1890s. '91 to '92, apparently. And people did this with light, beams of light, before they realized they're photons. And what happens with a beam of light, it's interesting, you know, comes a beam of light, the beam splitter sends half of the light one way, half of the light the other way. You already know with quantum mechanics that's going to be probabilistic. Some photons will go up, maybe some photons will go down, or something more strange can happen. If you have a superposition, some photons may go both up and down. So that's what can happen in quantum mechanics. We can get, if you send a beam, classical physics, it divides half and half and then combines, and there's an interference effect here. And we will design this interferometer in such a way that sometimes we can produce an interference that everything goes to D0, or everything goes to D1, or we can produce suitable interferences that we can get fractions of the power going into D1 and D2. D0 and D1. So we can do it in different ways, but we should think of this as a single photons going one at a time. You see, whatever light you put in here, experimentally, the same frequency goes out here. So what is interference? You might think intuitively that interference is one photon interfering with another one, but it can't be. If two photons would interfere in a canceling, destructive interference, you would have a bunch of energy that goes into nothing. It's impossible. If they would interfere constructively, you would add the electric fields and the amplitude would be 4 times as big because it's proportional to the square. So, but 2 photons are not going to go to 4 photons, cannot conserve energy. So first of all, when you get light interference, each photon is interfering with itself. It sounds crazy, but it's the only possibility. They cannot interfere with each other. You can send the photons one at a time. And therefore, each photon will have to be in both beams at the same time. And then each photon, as it goes along, there will be an interference effect, and the photon may end up here or end up there in a probabilistic way. So you have an example of superposition, a single photon state, a single photon is equal to superposition of a photon in the upper beam and a photon in the lower beam. It's like two different states, a little different from here. You had photons in two different polarization states superposed. Here you have photons in two different beams. A single photon is in both beams at the same time. And unless you have that, you cannot get a superposition and an interference that is consistent with the experiment. So what does that mean for superpositions? Well, it means something that we can discuss, and I can say things that at this moment may not make too much sense, but would be a good idea that you think about them a little bit. We associated states with vectors. States and vectors are the same thing. And it so happens that when you have vectors, you can write them as the sum of other vectors. So the sum of these two vectors may be this vector. But you can also write it as the sum of these two vectors. These two vectors add to this thing. And you can write any vector as a sum of different vectors. And that's actually quite relevant. You will be doing that during the semester, writing a state, a superposition of different things. And in that way, you will understand the physics of those states. So, for example, we can think of two states, A and B. And you see, as I said, states, wave functions, vectors, we're all calling them the same thing. If you have a superposition of the states A and B, what can happen? All right, we'll do it the following way. Let's assume if you measure some property on A, you always get value A. So you measure something, position, momentum, angular momentum, spin, energy, something. On A is a state that you always get A. Suppose you measure the same property on B, you always get B as the value. And now, suppose you have a quantum mechanical state, and the state is alpha A plus beta B. It's a superposition. This is your state. You superimpose A and B. And now you measure that property. That same property you could measure here, you measure it in your state. The question is, what will you get? You've now superposed those states. On the first state, you always get A. On the second state, you always get B. What do you get on the superposed states where alpha and beta are numbers? Complex numbers in general. Well, the most perhaps immediate guess is that you would get something in between, maybe alpha A plus beta B, or an average or something. But no, that's not what happens in quantum mechanics. In quantum mechanics, you always get A or you always get B. So you can do the experiment many times, and you will get A many times, and you may get B many times, but you never get something intermediate. So this is very different than in classical physics. If a wave has some amplitude and you add another wave of different amplitude, you measure the energy, you get something intermediate. Here not. You make the superposition, and as you measure, you will either get the little a or the little b, but with different probabilities. So roughly speaking, the probability to get little a is proportional to the number in front of here is alpha squared, and the probability to measure little b is proportional to beta squared. So in a quantum superposition, a single measurement doesn't yield an average result or an intermediate result. It leads one or the other. And this should connect with this thing of the photon we were talking before. If you think of the photon that was at an angle alpha in this way, you could say that the polarizer is measuring the polarization of the object. And therefore, what is the possible result? It may measure the polarization and say, oh, if it's in the x direction, you get it right. And what is the probability that you get it to be in the x direction is proportional to cosine squared alpha, the coefficient here squared. So the probability that you find the photon after measuring in the x direction is cosine squared alpha, and the probability that you'll find it here is sine squared alpha. And after you measure, you get this state, which is to say the following thing. The probability to get the value A is alpha squared, but if you get A, the state becomes A because this whole state of the system becomes that. Because successive measurements will keep giving you the value A. If you get B, the state becomes B. So this is what is called the postulate of measurement and the nature of superposition. This is perhaps the most sophisticated idea we've discussed today, in which in a quantum superposition, the results are not intermediate. So when you want to figure out what state you have to prepare many copies of your state in this quantum system and do the experiment many times, because sometimes you'll get A, sometimes you'll get B. After you've measured many times, you can assess the probabilities and reconstruct the state. We spoke about superposition, and we showed how when you have two states that are superimposed, the resulting state that is built up doesn't have properties that are intermediate between the two states that you're superimposing, but rather, when you do a measurement, you obtain the result that you would sometimes obtain the result that you would have with one of the states, and some other times with different probabilities, the results as if you had the other state. So it's a strange kind of way in which things are combined in quantum mechanics. So the next thing we have to say is a physical assumption that is made here, and it is that if you have a state and you superimpose it to itself, you haven't done anything. So the superposition of a state with itself has no physical import. So we can say this, it's a physical assumption, superimposing a state to itself does not change the physics. So if I have a state, A, this is physically equivalent, I'll write physically equivalent with this symbol, to the state A plus A, which would be 2 times A. It's physically equivalent to the state minus A. It's physically equivalent to the state IA. On anything is not equivalent to 0A, because that would be the 0 state. So it's physically equivalent as long as you have a non-zero coefficient. All these states are supposed to be physically equivalent. And that will eventually mean that we sometimes choose a particular one in those collection of states that is one that is convenient to work with, and that will be called a normalized state. A state that satisfies other properties having to do with the norm squared of the state. That will come later, but it's important that the number that is multiplying the physical state of your system has no relevance. And you could say, well, why all of a sudden you tell us this? Could this be shown to be necessary, or it's a physical assumption? So can we test it? Does it make some sense? And we can make some sense of this assumption at this level. And we do it with states of light. So remember, we spoke about photons hitting a polarizer, and we could speak of two independent kinds of photons. Photons polarized along the x-axis, and a photon polarized along the y-axis. And those are two quantum mechanical states. Now, suppose I decide to superpose those states to create the most general photon state. I would have an alpha, which is a number here, a complex number, and a beta there. And I would say, OK, here is my most general photon states. And how many parameters does this state have? It has two complex parameters, alpha and beta, and therefore 4 real parameters. And then you think about polarization states, how many parameters they have. And as we'll review in a second, it's well known that photons, their polarization state can be expressed with just 2 real parameters. So some counting is not going very well here. But here comes the help. If the overall coefficient here doesn't matter, if I can change it, I can multiply everything by 1 over alpha, and therefore get that the state is just the same, physically equivalent to this state, beta over alpha, photon, y. So all the physics is contained in this state as well. And if all the physics is contained in that state, I must look how many parameters it has. It still looks like there's 2 numbers here, but only the ratio appears. So if you call beta over alpha the number gamma, it's just 1 complex parameter. And therefore, thanks to this assumption, you now get that the most general photon polarization state has just 1 complex parameter, or just equivalently 2 real parameters. And that is the correct number. Indeed, if you have a polarization, a wave that has some polarization, the most general polarization state of a wave is an elliptical polarization. You probably did study a lot about circular polarizations. Maybe you also heard about the elliptical one, in which the electric field in a circular polarization, the electric field at any point traces a circle. But if you have an elliptical polarization, the electric field traces an ellipse. And that ellipse has an angle that is one parameter, and for an ellipse, the other since the size doesn't matter, the size depends just on the magnitude of the electric field. It's not a parameter of the polarization of the wave. Since the size doesn't matter, it's the shape of the ellipse that matters, and that's characterized by the eccentricity or by the ratio A over B of the semi-major axis, so parameters. Two parameters, and they are A over B and theta. So an elliptically polarized wave, which is the most general state of polarization of a wave, has two real parameters, and now, thanks to this physical assumption, we get this right. And this is important because that's something we're going to use all the time, that the overall factor in a wave function does not matter. So if we have superpositions, I want to emphasize one more thing about superpositions. And for that, I'm going to use spins. So what is spin? Spin is a property of elementary particles that says that actually, even if they're not rotating around some other particle, they have angular momentum. They have intrinsic angular momentum, as if they would be made of a tiny little ball that is spinning. I say as if, because nobody has ever constructed a model of an elementary particle where you can really make it spin and calculate how it works. Somehow this elementary particle has angular momentum, is born. Even if it is a point particle, it has angular momentum, and it's a spin. And spin is very quantum mechanical, and we can't quite understand it without it. So what happens is that you can measure the spin of a particle, and then if you measure it, you have to decide, however, since angular momentum is a vector, what direction you should use. And suppose you use the z direction to measure the spin of a particle, you may find that the particle has either spin up or the particle has spin down, spin. And the spin is the direction of the angular momentum. And that's the funny thing that happens with most matter particles. These are spin 1/2 particles. The spin can be up or can be down along the z direction that you measure. You measure it, and you never find it's 0 or a little bit. It's just either up with the full magnitude or down with the full magnitude. That is a spin 1/2 particle. And the state where it is up, we sometimes denote it with an arrow up and colon z, because it's up along z. And this would be down, an arrow down along z. But if those are possible quantum states, you could build a new quantum state by superposition, which would be up along z plus down along z. Now, if I wish to normalize it, I would put a factor in front of this. I will not talk about normalizations at this moment. They're not so important. If you are faced with this quantum state, so suppose you have an electron that is not in this state nor in this state, but is in this state, in a quantum superposition. So you go and you decide to try to measure it. Now, since you cannot predict what an electron is going to be doing, we cannot predict things in quantum mechanics with certainty, since we're going to do this experiment, avail ourselves of 1,000 copies of this electron. All of them in this peculiar quantum state. So you have the 1,000 copies, and you start measuring, and you decide to measure the spin in the z direction. And now what do you get? Well, we mentioned last time that you don't get an average, or since this is up and this is down, you get 0. You measure the first particle, and whoop, you find it up. Measure the second, up. The third, up. The fourth, down. Fifth, down. And then you get a series of measurements, and at the end of the 1,000 particles, you find about 495 up and 505 down. About half and half. And if you did with 10,000 particles, maybe it would be closer. Eventually, you find 50% in this state and find 50% in this state. And if you think this is strange, which you probably do, you could be justified, but here would come Einstein along and would say, all this stuff of this superposition is not quite right. You know, you had these 1,000 particles, but actually those 1,000 particles, half of them were with the spin up, and half of them were with the spin down. So here you have your 1,000 particles, your quantum state this, but Einstein says, no, let's make an ensemble of 1,000 particles, 500 up, 500 down, and do the same experiment, and the result is going to be the same. So how do you know you really have this, as opposed to somebody has given you 1,000 particles, 500 up, 500 down? How can you tell? And in fact, he would say even more. Whenever Einstein used the word realism to say, if I measure a spin and I find it up, is because before I measured it, the spin was up. It's almost like learning something about an object. If I look at this page and I find it color red, it's because before I looked at it, it was red. But then, in quantum mechanics, that doesn't seem to be the case. The state is this mix. And it was this mix before you measure, and after you measure, it's this. So there's no such thing as you learn by doing one measurement what the state of the particle was. So we will not resolve Einstein's paradox completely here, because we would have to learn more about spins, which you will do soon enough. But here is the catch that actually happens, is that if instead of having an ensemble of quantum states, you would have an ensemble of those states that half of them are up and half of them are down, you could now decide to measure the spin of the particle along the x direction. You take these particles and you measure along x. And what you will calculate with quantum mechanics later in this course is that if you measure along x, in these states, you will find all of them to be pointing along plus, up along x. All of them. While on this Einstein ensemble of 50% up and 50% down, you would find 50% up along x and 50% down along x. So there is an experiment that can tell the difference, but you have to look in another direction. And that experiment, of course, can be done, and it's a calculation that can be done, and you can decide whether these quantum states exist, and they really seem to exist. Let's talk now about entanglement. So we talk about entanglement when we have two non-interacting particles. You don't need a strong interaction between particles to produce entanglement. The particles can be totally non-interacting. Suppose particle 1 can be in any of these states, U1, U2. Let's assume just U1 and U2. And particle 2 can be in states V1 and V2. And you have these two particles flying around. These are possible states of particle 1 and possible states of particle 2. Now you want to describe the full system, the quantum state of the two particles. States of the two particles. Two particles. Well, it seems reasonable that to describe a state of the two particles, they're not interacting. I should tell you what particle 1 is doing and what particle 2 is doing. Okay, so particle 1 could be doing this, could be U1. And particle 2 could be doing V1. And in a sense, by telling you that, we've said what everything is doing. Particle 1 is doing U1, particle 2 is doing U2. And mathematically, we like to make this look like a state, and we want to write it in a coherent way. And we sort of multiply these two things. But we must say sort of multiply, because a strange multiplication, this, you know, we think of them as vectors or states. So how do you multiply states? So you put something called a tensor product, a little multiplication like this. So you could say, don't worry, it's kind of like a product. And it's the way we do it. We don't move things across. We list the first state here, the second state here, and that's a possible state. Now, I could have a different state, because particle 1, in fact, could be doing something a little different. Could be doing alpha 1 U1 plus alpha 2 U2. And maybe particle 2 is doing beta 1 V1 plus beta 2 V2. And this would be all right. I'm telling you what particle 1 is doing, and I'm telling you what particle 2 is doing. And the rules of tensor multiplication, or this kind of multiplication to combine those states, are just like a product, except that, as I said, you never move the states across. So you just distribute. So you have alpha 1, beta 1, the number goes out, U1, V1. That's the first factor, plus alpha 1, beta 2, u1, v2, plus alpha 2, beta 1, u2, v1, plus alpha 2, beta 2, u2, v2. I think I got it right. Let me know. Alpha 2, beta. I just multiplied and got the numbers out. The numbers can be moved out across this product. Okay, so that's a state, and that's a superposition of states. So actually, I could try to write a different state now. You see, we're just experimenting, but here is another state, u1, v1, plus u2, v2. Now, this is a state that actually seems different. Why different? Because I don't seem to be able to say that what particle 1 is doing and what particle 2 is doing separately. You see, I can say when particle 1 is doing u1, particle 2 is doing v1. And when particle 1 is doing u2, this is v2. But can I write this as some state of the first particle times some state of the second particle? Well, let's see. Maybe I can and can write it in this form. This is the most general state that you can say. Particle 1 is doing this, and particle 2 is doing that. So can I do that? Well, I can compare these two terms with those, and I conclude that alpha 1, beta 1 must be 1. Alpha 2, beta 2 must be also 1. But no cross products exist, so alpha 1, beta 2 must be 0, and alpha 2, beta 1 must be 0. And that's a problem because either alpha 1 is 0, which is inconsistent, or beta 2 is 0, which is inconsistent with that. So no, this state is unfactorizable. It's a funny state in which you cannot say that this quantum state can be described by telling what the first particle is doing and what the second particle is doing. What the first particle is doing depends on the second, and what the second is doing depends on the first. This is an entangled state. And then we can build entangled states, and are very strange states. So with two particles with spins, for example, we can build an entangled state of two spin 1/2 particles. And this state could look like this. The first particle is up along z, and the second particle is down along z, plus a particle that is down along z for the first particle, but the second is up along z. And these are two spin 1/2 particles, and in the usual notation, these experiments in quantum mechanics, in black hole physics, people speak of Alice and Bob. Alice has one particle, Bob has the other particle. Maybe Alice is in the moon and has her electron, and Bob is on Earth and has his electron. And the two electrons, one in the Earth and in the moon, are in this state. So then we say that Alice and Bob share an entangled pair. And all kinds of strange things happen. People can do those things in the lab, not quite one in the Earth and one in the moon, but one photon at one place and another photon entangled with it at 100 kilometers away. That's pretty doable. And they are in this funny state in which their properties are correlated in surprising ways. So what happens here? Suppose Alice goes, or let's say Bob, goes along and measures his spin. And he finds his spin down. So you look here, here is down for Bob. So at this moment, the whole state collapses into this, because up with Bob didn't get realized. So once Bob measures and he finds down, the whole state goes into this. So if Alice on the moon or in another galaxy at that instant looks at her spin, she will find it up before light has had time to get there. Instantaneously, it will go into this state. People were sure somehow this violates special relativity. It doesn't. You somehow, when you think about this carefully, can't quite send information, but the collapse is instantaneous in quantum mechanics. Somehow Bob and Alice cannot communicate information by sharing this entangled pair. But it's an interesting thing why it cannot happen. Einstein again objected to this, and he said, this is a fake thing. You guys are going to share, and now, of course, they have to share many entangled pairs to do experiments, so maybe 1,000 entangled pairs. And Einstein would say, no, that's not what's happening. What's happening is that some of your entangled pairs are this. That is, Alice, Bob is down, Alice is up. Some of them are this. And there's no such thing as this entanglement. And indeed, if you measure and you find down, she will find up. And if you measure and you find up, she will find down. And there's nothing too mysterious here. But then came John Bell in 1964 and discovered these Bell inequalities that demonstrated that if Alice and Bob can measure in 3 different directions, they will find correlations that are impossible to explain with classical physics. It took a lot of originality for Bell to discover this, that you have to measure in 3 directions. And therefore, the kind of correlations that appear in entangled states are very subtle and pretty difficult to disentangle. So that's why entanglement is a very peculiar subject. People think about it a lot because it's very mysterious. It somehow violates classical notions, but in a very subtle way. Mach-Zehnder interferometers. And we have a beam splitter, and the beam coming in, it splits into 2, a mirror, another mirror. The beams are recombined into another beam splitter, and then 2 beams come out, one into a detector D0 and a detector D1. We could put here any kind of devices in between. We could put a little piece of glass, which is a phase shifter. We'll discuss it later. But our story is a story of a photon coming in and somehow living through the interferometer. And we want to describe this photon in quantum mechanics, and we know that the way to describe it is through a wave function. But this photon can live in either of two beams. If a photon was in one beam, I could have a number that tells me the probability to be in that beam. But now it can be in either of two beams. Therefore, I will use two numbers, and it seems reasonable to put them in a column vector. Two complex numbers that give me the probability amplitudes for this photon to be somewhere. So you could say, oh, look here. What is the probability that we'll find this photon over here? Well, it may depend on time. By the time the photon is gone, it's gone. But when it's crossing here, what is the probability? And I have two numbers. What is the probability here? Here, 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 here. And in fact, you could even have one photon that is coming in through two different channels as well. So I have two numbers. And I want now to do things in a normalized way. So this will be the probability amplitude to be here. This is the probability amplitude to be down. And therefore, the probability to be in the upper one, you do norm squared. The probability to be in the bottom one, you do norm squared, and you get 1. Must get 1. So if you write two numbers, they better satisfy that thing. Otherwise, you're not describing probabilities. OK, so on the other hand, I may have a state that is like this, alpha. Oh, I'll mention other states. State 1, 0 is a photon in the upper beam. No probability to be in the lower beam. And a state 0, 1 is a photon in the lower beam. So these are states, and indeed, think of superposition, and we have that the state alpha beta, you know how to manipulate vectors, can be written as alpha 1, 0, because the number goes in and becomes alpha 0, plus beta 0, 1. So the state alpha beta is a superposition with coefficient alpha of the state in the upper beam plus a superposition with coefficient beta of the state in the lower beam. We also had this little device, which is called the beam shifter of phase delta. If the probability amplitude is alpha to the left of it, it's alpha e to the I delta to the right of it, with delta a real number. So this is a pure phase. And notice that alpha is equal to e to the I delta. The norm of a complex number doesn't change when you multiply it by a phase. The norm of a complex number times a phase is the norm of the complex number times the norm of the phase, and the norm of any phase is 1. So actually, this doesn't absorb the photon, doesn't generate more photons, preserves the probability of having a photon there, but it changes the phase. So how does the beam splitter work, however? This is the first thing we have to model here. So here is the beam splitter. And you could have a beam coming, 1, 0 beam hitting it, so nothing coming from below, and something coming from above, and then it would reflect some and transmit some. And here is a 1, is the 1 of the 1, 0, and here's an S and a T, which is to mean that this beam splitter takes the 1, 0 photon and makes it into an ST photon, because it produces a beam with S up and T down. On the other hand, that same beam splitter, now we don't know what those numbers S and T are. That's part of designing a beam splitter. You can ask the engineer what are S and T for the beam splitter, but we are going to figure out what are the constraints, because no engineer would be able to make a beam splitter with arbitrary S and T. In particular, you already see that if a photon comes in, probability conservation, there must still be a photon. You need that S squared plus T squared is equal to 1, because that's a photon state. Now, you may also have a photon coming from below and giving you a UV, so this would be a 0, 1 photon, giving you a UV. And therefore, we would say that 0, 1 gives you UV, and you would have U plus V, norm squared, is equal to 1. So we need apparently 4 numbers to characterize the beam splitter. And let's see how we can do that. Well, why do we need really 4 numbers? Because of linearity. So let's explore that a little more clearly. And suppose that I ask you, okay, so what happens to an alpha beta state, if it enters the beam splitter? What goes out? Well, the alpha beta state, as you know, is alpha 1, 0 plus beta 0, 1. And now we can use our rules. Well, this state, the beam splitter, is a linear device, so it will give you alpha times what it makes out of the 1, 0. But out of the 1, 0 gives you ST. And the beta times 0, 1 will give you beta UV. So this is alpha S plus beta U times alpha T plus beta V. And I can write this actually as alpha beta times the matrix SU TV. And you get a very nice thing, that the effect of the beam splitter on any photon state alpha beta is to multiply it by this matrix SUTV. So this is the beam splitter. The beam splitter acts on any photon state, and out comes the matrix times the photon state. This is matrix action, something that is going to be pretty important for us. So, how do we get those numbers? After all, the beam splitter is now determined by these 4 numbers, and we don't have enough information. So the manufacturer can tell you that maybe you bought a balanced beam splitter, which means that if you have a beam, half of the intensity goes through, half of the intensity gets reflected. That's a balanced beam splitter. That simplifies things, because the intensity here, the probability to get this particle must be the same as that. So each norm squared must be equal to 1/2 if you have a balanced beam splitter. And you have S squared equal T squared equal U squared equal V squared equal 1/2. But that's still far from enough to determine S, T, U, and V. So rather than determining them at this moment, might as well do a guess. So can it be that the beam splitter matrix, could it be that the beam splitter matrix is 1 over square root of 2, 1 over square root of 2, 1 over square root of 2, and 1 over square root of 2? That certainly satisfies all of the properties we've written before. Now, why could it be wrong? Because there could be pluses or minuses, or there could be i's, or anything there. But maybe this is right. Well, if it is right, the condition that it be right is that if you take a photon state, one photon, after the beam splitter, you still have one photon. So conservation of probability. So if you act on a normalized photon state that satisfies this alpha squared plus beta squared equal 1, it should still give you a normalized photon state. And it should do it for any state. And presumably, if you get any numbers that satisfy that, some engineer will be able to build that beam splitter for you because it doesn't contradict any physical principle. So let's try acting on this on this state, 1 over square root of 2, 1 over square root of 2. Let's see. This is normalized. 1/2 plus 1/2 is 1. So I multiply. I get 1/2 plus 1/2. I get 1 and 1. Sorry, this is not normalized. 1 squared plus 1 squared is 2, not 1. So this can't be a beam splitter. No way. So we try minus 1 over square root of 2. Actually, if you try this for a few examples, it will work. So how about if we try it in general? So if I try it in general, acting on alpha beta, I would get 1 over square root of 2, alpha plus beta, and alpha minus beta. Then I would check the normalization. So I must do norm of this 1 squared. So it's 1/2 alpha plus beta squared plus 1/2 alpha minus beta norm squared. Well, what is this? Let me go a little slow for a second. Star plus beta star plus alpha minus beta, alpha star minus beta star. Well, the cross terms vanish. And the alpha, alpha star, beta, beta star, beta, beta star add. So you do get alpha squared plus beta squared. And that's 1 by assumption, because you started with a photon. So this works. This is a good beam splitter matrix. It does the job. So actually, I'll consider this beam splitters. And actually, it's not the unique solution by all means. But we can have 2 beam splitters that differ a little bit. So I'll call beam splitter 1 and beam splitter 2. Beam splitter 1 will have this matrix. And beam splitter 2 will have the matrix we found here, which is a 1, 1, 1, minus 1. So both of them work, actually. And both of them are good beam splitters. I call this beam splitter 1, and this beam splitter 2, and we'll keep that. And so we're ready now to think about our experiments with the beam splitters. And let me assume, for example, that I'll put a state alpha beta in. what do I get out? So you have the state alpha beta. What do you get out? Well, state comes in and is acted by beam splitter 1. So you must put the beam splitter 1 matrix. And then it comes the mirrors. And let's assume mirrors do nothing. In fact, mirrors, the two mirrors would multiply by -1, which will have no effect. So let's ignore mirrors. And then you get to beam splitter 2, and you must multiply by the matrix of beam splitter 2, and that's the output. And that output is a two-component vector that gives you the amplitude up and the amplitude down. So I should put BS2 here. BS1 over here, alpha beta. The numbers move away, 1 over square root of 2 and 1 over square root of 2, commute in matrix multiplication. And then you multiply these two matrices, you get 0, 2, -2, and 0. Alpha beta, and you put the 2 in, so you get beta minus alpha. So here is the rule. If you have alpha and beta, you get here beta and minus alpha here, or a beta minus alpha photon at the end. Good. So let's do our first kind of experiment. Our first experiment is to have the beam splitters here. D0, detector D0, and detector D1 over there. And let's send in a photon over here only. 1, or input 0, 1. Well, this photon, 0, 1, splits here. You act with BS1, the matrix BS1, you get two things. You act with the matrix BS2 and it gives you this. But we have the rule already. If you have an alpha beta, out comes a beta minus alpha. So it should have a 1 here and minus 0 here, which is 0. So you get a 1, 0. So what is really happening? What's really happening is that your photon that came in divided in two, recombined, and actually there was a very interesting interference here. From the top beam came some amplitude and gave some reflected and some transmitted. From the bottom beam, there was some transmission and some reflection. The transmission from the top and reflection from the bottom interfered to give 0. And these two, the reflection from the top and transmission from the bottom, were coherent and added up to 1. And every single photon ends up in D0. If you would put a beam, well, Mach and Zehnder were working in the late 1800s, 1890s, and they would shine light. They had no ability to manipulate photons, but they could put those beam splitters, and they could get this interference effect where everything goes to D0. So far, so good. Now let me do a slightly different experiment. I will now put the same thing, a BS1 and a beam going in, mirror, mirror, BS2 here. But now I will put a block of concrete here on the way. I'll put it like this. So that if there's any photon that wants to come in this direction, it will be absorbed. Photon could still go like this, but nothing would go through here. And here, of course, there might be D0 and D1. And here are the mirrors, M and M. Now, the bottom mirror is of no use anymore because there's a big block of concrete that will stop any photon from getting there. And we are asked again, what happens? What do the detectors see? And this time we still have a 0, 1. Now, I would be tempted to use this formula, but this formula was derived under the wrong assumptions, that there was no block here. So I cannot use that formula, and certainly things are going to be different. So I have to calculate things, and we're doing a quantum mechanical calculation. So, well, up to here, before it reaches here, I can do my usual calculation. It's certainly we have BS1 acting on the state 0, 1. And this is 1 over square root of 2, I think, minus 1, 1, 1, 1. Yep, that's BS1. Acting on 0, 1. And that gives me 1 over square root of 2, 1 over square root of 2. So, yes, here I have 1 over square root of 2 amplitude, and here I also have 1 over square root of 2 amplitude. Okay. Now that's the end of this amplitude. It doesn't follow. But on the other hand, in this branch, the mirror doesn't change the amplitude, doesn't absorb. So you still have 1 over square root of 2 here. And now you're reaching BS2. Now what is the input for BS2? The input is a 1 over square root 2 in the top beam and nothing in the lower beam because nothing is reaching BS2 from below. This is blocked. So yes, there was sometimes when something reached from below, but nothing here. So to figure out the amplitudes here, I must do BS2 acting on 1 over square root of 2, 0. Because 1 over square root of 2 is coming in, but nothing is coming in from below. And therefore, I get 1 over square root of 2, 1, 1, 1 minus 1, 1 over square root of 2, 0. This time I get 1/2 and 1/2. Okay, we must trust the math. 1/2 here and 1/2 there. So 1/2, a column vector, 1/2, 1/2. Okay, let me maybe tabulate this result, which is somewhat strange, really. So what is strange about it is the following. In the first case, where the interferometer was totally clear, nothing in the middle, everything went to D2, and nothing went into D1. But now you do something that should block some photons. You block some photons in the lower path, and now you seem to be able to get something into D1. There is an amplitude to get into D1. So by blocking a source, you're getting more somewhere. It's somewhat counterintuitive. You will see by the end of the lecture in 10 minutes that it's not just somewhat counterintuitive, it's tremendously counterintuitive. Let's summarize the result here. The outcome come in the blocked lower branch case, and the probability for those events. So photon at the block. The photon can end in 3 places. It can end on the block, it can end on D0, or it can end on D1. So photon at the block, well, the amplitude to be here is 1 over square root of 2. The probability should be 1/2. Photon at D0, probability amplitude 1/2, probability 1/4. Photon at D1, probability 1/4. You could put another table here, outcome, all open, probability, and in this case there's just photon at D0 was 1, and photon at D1 was 0. So far, so good. So here is the kind of very entertaining thing that happens when you try to do some physics with this. And this was done by 2 physicists, Elitzur and Weidmann in Tel Aviv. They invented or fantasized about some sort of bombs, things that explode. So they're called Elitzur, Weidmann bombs. And you could invent different things, but here is what a Elitzur-Weidmann bomb is. Some sort of bomb. And the way it works is with a photon detector. So there's a little tube in the bomb, and there's a photon detector. And you have your bomb, and you want to detonate it. You send the photon in. You send the photon in through the tube, and the photon, it's detected by the detector, and the bomb explodes. On the other hand, if the bomb is defective, the photon goes in, and the detector doesn't work, the photon goes out. Just goes through. So that's an Elitzur-Weidmann bomb. And here is the puzzle for you. Suppose you have those bombs, and unfortunately, those bombs, after time, they decay, and sometimes the detectors go wrong, and they don't work anymore. So you have 10 bombs, and maybe 5 have gone wrong. And now you have maybe a very important mission, and you need a bomb that really works. So what do? Let's assume you cannot break apart the detector. It's just too complicated. So you have the bombs, and you want to test them. If you send in a photon and nothing happens, the bomb is not working. But if you send in a photon and the bomb is working, explodes. So you cannot use it anymore. So the question that Elitzur and Weinman pose, is there a way to certify that the bomb is working without exploding it? Can you do that? The answer looks absolutely impossible. And certainly in classical physics, it's completely impossible. You either do the measurement to see if the detector works, and if it works, your lab goes off. It's totally destroyed. And if it doesn't work, well, okay, it's not a good bomb anyway. So there's no way out. But there is a way out, and it is to insert this bomb in the Mach-Zehnder interferometer. So here we go. We put the Mach-Zehnder interferometer. And we insert the bomb here with the detector along this place. D0 and D1 are still here. And now you put this and you send in a photon. So let's see what happens if you send in a photon. Suppose the bomb is defective. Bomb is defective. So what are the possible outcomes? Outcome and probability. Photon goes to D0. 0. Photon to D1. Bomb explodes. Well, we said the bomb is defective. So if the bomb is defective, we said it's like a detector that doesn't work and lets the photons go through. So if the bomb is defective, this as if there's no bomb here, and you'll have the situation where all is open. So there will be a probability of 1 to get the photon to D0, a probability of 0 to get the photon to D1, and the bomb, of course, doesn't explode, probability of 0. On the other hand, suppose the bomb is good. Bomb is good. It's good. And then what are the outcomes? And what are the probabilities? Well, you know more or less what's happening already. The bomb is good means there is a detector that never fails to detect the photon. And if a photon comes in, it will capture it. It will block it. The bomb will explode. So you have your Mach-Zehnder interferometer, and you've really done the equivalent of this if the bomb is really working. You've put a block of concrete. It's going to absorb the photon. So if the bomb is really working, the outcome are the following. Well, I'm sorry to say your lab will explode half of the times. because the photon at the block happens and bomb explodes with probability 1/2. On the other hand, in this situation, it is possible that a photon at d0 and bomb doesn't explode. Not explode. And there's a probability 1/4. And there's a probability 1/4 that the photon is at d1 and the bomb does not explode. But here is the catch now. Yes, half of the bombs exploded. We're sorry about that. But if the bomb doesn't work, there is no way a photon can reach d1. Because if a bomb doesn't work, all photons go to d0. So the fact that some photons, 1/4% of the time, 25% of the time, reach d1 implies that photon is at d1 and bomb did not explode, but the bomb is good. So look what has happened. It's really strange. The photon the bomb was here, it was ready to explode. The photon skipped the bomb and ended in d1, and you still know that the bomb works now, even though the photon never went through the detector. It never touched here. It never went inside and get detected. Somehow it went through the other way, but you know that the bomb is working with 1/4% efficiency. We will do exercises, and it's possible to raise the efficiency to 50%. And if you put the bomb inside a cavity, a resonant cavity with photons going around, you can reach 99% efficiency. So the probability of blowing up MIT goes down to 1%. I don't know if we can live with that. I don't think so. But anyway, this is a true fact. Experiments without bombs have been done, and it shows that in quantum mechanics you can do very surprising measurements. Last time we spoke about photons in the context of an interferometer, the Mach-Zehnder interferometer. And we saw the very unusual properties of photons and interference, and how a relatively simple interference effect can be used to produce a very surprising measurement. Today we're going to backtrack and go from the beginning and think about photons as physicists did 100 years ago, and how by thinking about photons, they pretty much came up with quantum mechanics. So we want to trace this back, and the best place to start probably is with a photoelectric effect. The photoelectric effect is an experiment done by Hertz in 1887, in which he irradiated plates, that means shine light, high energy beams of light on metal plates, and he found that electrons were released. Those were called photoelectrons, and therefore you would get a photoelectric current from those electrons. So this is the effect we want to discuss now. It's the photoelectric effect. And it's Hertz, 1887. So first the description. So polished metal plates, irradiated may emit electrons. And these are called photoelectrons sometimes. Photoelectrons is just an electron that was released due to a photon. And therefore, we get a photoelectric current. Photoelectric current. OK, so so far so good. But what was special about this experiment? The first step that was special was that there was a critical frequency. If you would take a sample and you would irradiate it with light, and you would begin with light with very low frequency, nothing would happen. And all of a sudden, after a certain frequency, boom, you would get a current. So there is a threshold frequency. There is a threshold frequency, nu zero, such that only for nu greater than nu zero, there is a current. So no current for lower frequencies. Now, as it turned out, nu zero depends on the metal you're irradiating. And even more, it's a complicated thing to calculate. It depends on the surface of the metal, so that's why Hertz apparently had to polish the metal. And this frequency, if the metal is irregular, may depend on where you shine. So you better prepare the metal very nicely, and it may even depend on the crystalline nature of the metal, because it's a many-body effect. You see, anticipating the resolution, there's this piece of metal, and there are a few free electrons running around, and they run around among the crystalline structure of the metal, and removing them, it's going to take some energy, and that energy depends on the metal and the arrangement and all kinds of things. So this nu zero depends on the metal, and the configuration, abbreviate, of atoms at the surface. Third property was kind of interesting. The magnitude of the current was proportional to the intensity of the light. Magnitude. Current is proportional to the light intensity. To the light intensity. And perhaps the last one and fourth, a rather important one, a very crucial property, is that you could observe the energy of the photoelectrons, and it seemed to be independent of the light intensity. So energy of the photoelectrons is independent of the intensity of light. The number of photoelectrons would depend on the intensity of light, but not the energy of the photoelectrons. Now, there's more to that, but I think it was not quite exactly noticed by Hertz. So Hertz probably did notice all these things, but the last one that maybe we can put in brackets here is that the energy of the photoelectrons, E gamma, oh no, bad idea, E of the electrons, increases linearly with the frequency of the light. So this photoelectric effect was not easy to understand if you thought of light as a wave. And Einstein came up with an answer that he almost said what was going on, but didn't quite use the word. He said that light comes in bundles of energy, and in a beam you have bundles of energy, quanta. Didn't quite say there's light is a particle. He himself was a little non-committal, I think, about this concept. But Einstein in 1905 gives the natural explanation. It says that light